In this video, we'll go over the answer key for Wednesday, April 22nd. And we start with redox reactions. Now, we've talked about redox reactions previously in general chemistry. Now we're going to look at how we balance redox equations. And we have a whole formula here that will help us do that. So the first one is just to decide the oxidation states. And so what I'm going to do is C, because C is the more difficult one. And just going back, you want to determine the oxidation states to see what element was oxidized and which one's reduced. Now, I actually didn't do that because you can figure out the oxidation states, I think, much easier after you split the reactions in half. So what I did is actually write half reactions. So I have BrO3 minus going to Br minus, and N2H4 going to N2. Now the way you write half reactions is that the elements should more or less stick together in the same half reaction. So Br with Br and nitrogen with nitrogen. Alright, so once you have your half reactions, now we have to balance our half reactions. So the first thing we need to do is balance any element other than oxygen and hydrogen, which is already done. Then we need to balance oxygens by adding water. So in BrO3, there's 3 oxygens. So on the other side of the equation, I balance that by adding 3 waters. And now there's no oxygens at N2H4, so now we want to balance the hydrogens. So going back to BrO3 minus, I have 6 hydrogens on the right side. So I need to put 6 hydrogens on the left side as well. So now my hydrogens balance out. Importantly, do not forget that hydrogens have a +1 charge. For N2H4, I do the same thing. I have 4 hydrogens on the left. I need to put 4 hydrogens on the right. Right, and if your reaction's in a basic solution, neutralize the H plus with OH minus. So that would be explicitly said. I would say this solution is basic, and that's when you do that. Here, though, I want to balance, go to step 4, balance my charges by adding electrons. So let's look at the BrO3 example. I have 6 plus 1 charges and 1 minus 1 charge in my reactants. Overall, the charge on the left side of the equation is +5. On the left side of the right side of the equation, I have a -1 and a 0. Overall, the charge is -1. So I need the charges to be the same on both sides of the equation. I'm going to do that by adding 6 electrons to the left side. So 6 -1 charges for my electrons plus 6 +1 for my hydrogens. These cancel out because those are both 6 but opposite sign. I'm left with a minus charge and a minus charge. I do the same thing for the other side of the equation. I have 4 pluses on my right hand side, no charge on the left side of the equation, so I add 4 electrons. Now before combining these half equations back into a normal equation, I need to make sure the electrons are the same, the number of electrons are the same in each equation. So in one equation I have 4, and the other one I have 6. So I'm going to make these both 12 by multiplying the N2H4 equation by 3 to give 12 electrons, and the BrO3 equation by 2 to give 12 electrons. So that's what I did here. Multiplied this equation by 2 to get 12 electrons plus 12 hydrogens plus 2 BrO3 minus goes to 2 bromine plus 6 hydrogens. The right side I get 3 N2H4 plus 3 N2 plus 12 H2 plus 12 E minus, because remember I multiplied by 3. Once the number of electrons are the same, you can recombine this equation. Anything on the left side of the arrow must remain on the left side. Anything on the right side of the arrow must remain on the right side. And then you can cancel terms. So I have 12 electrons as a reactant and 12 electrons as a product. If they both end as a reactant and a product, I cancel them out. Same thing with these hydrogens. And then at the very end, I'm left with 2 BrO3 minus plus 3 N2H4 goes to 2 Br minus plus 6 water plus 3 nitrogens. And what you should also do is make sure this is still balanced, the charges are balanced, and the masses are balanced as well. And that is how you balance redox reactions. Now let's see how redox reactions happen. And they can happen in a voltaic cell. And this is basically how batteries work. We connect one cell that is doing an oxidation reaction. Remember, oxidation is loss of electrons. We connect that to another cell that will go through a reduction reaction. A reduction is a gain of electrons. Then we connect these two anodes through with a cable. And the electrons want to go from oxidation to reduction. And along that path, we can use their energy to do work, like light a light bulb. During this process, we also need a salt bridge. We're going to get a buildup of ions on each side. So you can see on the left side, we are getting a buildup of +2 ions. And on the right side, we are losing ions. So if we don't have a way to neutralize these ions, the reaction will not go at all, because the electrons will no longer want to flow. So the salt bridge just allows ions to pass to each side of our voltaic cell. So we're just going to get practice here doing a voltaic cell, writing down what they look like with my not so great drawing. And so I did A for us. So the first thing we need to do for A is figure out what is gaining electrons, what's losing electrons. And we can do that by the charge. So here silver on the left side is plus, and then it goes to neutral. The only way you go from +1 charge to 0 charge is by gaining an electron. And lead to 2 plus lead. So I lost 2 charges. I went from 0 to +2. And the only way I can go more positive is by losing electrons. So since silver is gaining electrons, it is being reduced and is my cathode. Lead is losing electrons, it's oxidized, it's my anode. So I'm going to write my anode on the left, cathode on the right. The solid phases are what I have drawn here. Those are my electrodes, so solid lead, solid silver. In solution, you're going to have lead 2 plus and silver plus. The electrons are going to flow from the lead to the silver, and that is my salt bridge. And that is how you draw a voltaic cell. And that's it for this video. I will see you in the next one.